Okay, now we're going to be talking about the cubic equation. So most of you guys have probably known the quadratic equation for quite some time now. We're going to do an example of the cubic equation. This is, well, it has a very rich history, as you guys will read in the book. Sometimes attributed to Cardano in his book. But in any case, you guys will read about Cardano and Tartaglia and all that stuff. Historically, let's do an example with real numbers of using the cubic equation. So let's say we start with something like this. X cubed plus 3x equals 36. So whatever's here and whatever's here, this becomes our m and this becomes our n. And we're going to need to know n over 2, which is 18, and we are going to need to know m over 3, which is equal to 1. We're also going to need to know n over 2 squared, because I see that appears in the formula, and I'm looking at the formula right here on page 273 of Eves, which is our text. So we'll take n over 2 squared, and I got for that 324. And m over 3 cubed, well, this one's really easy. That is 1. So I'm going to end up with an n squared and an n over 2 squared and an m over 3 cubed together. If I plug that into the formula, what do I end up with? I'm going to have a square root of 325, and that's going to appear twice. Now, of course, that's not our answer. That's just going to be the square root on the inside of those formulas I have there for a and b. So I end up with the cube root of n over 2, which is 18, plus 325 and a square root. That's our a. And then a minus 18 plus the square root of 325. That is our b. And that's actually going to give us, if we plug this into something, say, like Wolfram alpha, I get, well, decimal approximation 2.999999999. It's telling us that the answer here is actually going to be 3 for our a minus b. This is an example of the cubic equation. As you guys would have expected, it is considerably more complicated than the quadratic equation. Also, you guys will notice that there's no coefficient of x squared here. And that's because every cubic can be reduced to one that has no quadratic term. But this in itself could take some steps. Of course, it does take some steps to begin with. So things aren't as simple for the cubic, and for the quartic, for the fourth degree equations, they're even more difficult if you want a solution involving square roots and things. Now, for the fifth degree equation, and this is something that you guys will read about a little later, there are some problems that come up when you get to equations of the fifth degree. And it's not that no equation of the fifth degree has solutions. I mean, clearly, x to the 5 minus 1 has a solution. I plug in 1, and that gives me a root, right? Root of 0. But the issue is there aren't always solutions that are expressible using the simple systems, the simple symbols that we have for the quadratic, cubic, and quartic formulas. That is, if you introduce a little bit of new notation, I mean, you could always introduce a symbol, right, for the fifth root of any equation. The important thing to know about this is that the symbols, extra symbols are required. There is no simple solution involving just roots and just plus, minus, times, divides, that sort of thing for the fifth degree equation. And this was something that was very unexpected. Mathematicians did not seek out to prove that there was no solution in the very beginning. Mathematicians originally wanted a solution to equations, polynomial equations of all degrees. But mathematics is discovered, and regardless of what we want in mathematics, sometimes we have to settle, well, always in mathematics, we have to settle for what is true.